Welcome to Applied Mathematical Finance. So now we start a new subsection in our section on interest rate products. So what we had last time was products without optionality, and I already made the remark that this section is a little bit linear products. So linear products, okay, that's maybe right. It was a linear function of a martingale, yeah, paying in a certain unit. It was a special situation, and we could value all linear functions of this index. Put differently, we could also say that this is the class of products that may be valued without a model assumption. So model means specifying the stochastic process for the underlying quantities. So the section we will look at today, so these guys here, are to some extent nonlinear product. Well, the simple nonlinear product will be the option that is actually this payoff here, yeah. So it has a little kink, yeah, the maximum of S minus K and 0, yeah, so the call option. So you could say this is a piecewise linear product, and this section is a little bit about valuing the piecewise linear products, and these are products where the product valuation requires a model, but still this section is a little bit special because we will make a special model assumption that allows us to derive an analytic formula for the evaluation. Yeah. Black-Scholes formula, Bachelier formula, something like this. We can do this actually for many guys here, yeah. So we can do this for the cap, for the Swaption, yeah, also for the Quanto Caplet, and assuming another special model also for the Quanto Caplet, and also to some extent for the options on the backward rate. Well, the third thing, so the next step after this are complex models or products where we do not have an analytic formula and where we need a numerical method, yeah, like a Monte Carlo method to approximate the integral. Yeah, already here, if you know how to value a piecewise linear function with an analytic formula, then you immediately can think of a numerical method that can value arbitrary functions, because you approximate the arbitrary function by a piecewise linear function and then combine all your analytic formulas, yeah, like you approximate an integral by a Riemann sum, yeah, a finite sum. You have then a sum of such analytic formulas. So you see, we are going step by step to more complex products. The section I will do today is, well, rather a collection of definitions. I go through all these different products, also explain you which product is maybe important, yeah, in the sense that it is liquid on the market. It's an important product for the industry. And also this section is still, in this sense, single curve. Oops, sorry. So single curve means that we assume there is a single interest rate curve observed in the market. There's a single family of zero coupon bonds spanning the interest rate curve, and everybody can trade in this curve. Then in the end, so maybe after this section, yeah, or after the next two ones, yeah, we discuss how to move away from this, how to create a richer, more realistic structure, a multi-curve world. And funny thing is that the technique allows us to fall back to the single curve theory, which is collateralization, which is also a standard in the market that makes life easy again. So that will be interesting. So just to avoid that you have the feeling you are learning some idealized stuff that is not relevant. Actually, all this stuff is very relevant. So let's start looking at these products with optionalities. We are looking at interest rate products. So the first one is the caplet. So the caplet is just an option on the forward rate L. So maybe you remember we have here the forward rate L. We fix at the beginning of the period. So this is here the fixing time. We pay again at the natural point at the end of the period. So it's like in the floater or like a single payment in a swap. Here we exchange a floating payment against a fixed payment. So we exchange this against K and we pay at capital T2 at the end of the period. So if you like to draw your little periods here, there's T1 where we fix the rate, T2 where we pay the rate, and the L is the rate for this period. So you see there's also here our day count fraction or year fraction multiplied to this payment. So this rate here is in the unit per time. Multiplying with time is a unitless quantity. So we multiply with the amount that we pay at the end. This is my notion. So you see, this is just the call option. So like a call option on a stock, the classical payoff. So this is like a call option on a stock. A cap is just a collection of caplets. So a cap is a portfolio of caplets. So you have some tenor discretization. So I have some time discretization. And now on this time discretization, I observe different caplets from T1 to T2, from T2 to T3, and so on. Okay, so since this is just a portfolio, a sum of such caplets, well, the valuation is clear. It's just the sum, the value of the cap is just the sum of the values of the caplets. There is maybe a small nuance in the market. For a caplet, you could specify here a rate K, which is called the at-the-money rate, which coincides with the today's observed forward rate, so which will be the L of here T0. And this is somewhat a special guy because it is more or less, the distribution is more or less centered at what we expect today. And for this guy, for the caplet, you have here in theory the possibility to choose caplets with different strike rates. But what is usually done in the market is that the strike rate for all these caplets is the same. So if you have an interest rate curve that has a certain slope, so then you are taking some kind of average level. So one of these will be out of the money. Some of these will be out of the money. So where K is maybe below L or above L, and some of them are in the money. So where the K is then below L. Okay, so just a call option. This is the caplet, an option on the forward rate. A floorlet is just the opposite. So while the caplet pays you if the interest rate goes up, yeah, it pays you if you get above K, the floorlet pays you the amount that you are below K. So a floorlet is just the pay of K minus L, so maximum of K minus L and 0, of course, multiplied with the period length and your notional. Okay, so this looks like what you might know from equity. So it looks like, oops. So it looks like a put, yeah. So it is that I can sell for a given price. Maybe the names caplet and floorlet appear a bit counterintuitive. Yeah. So if you think of functions which you sometimes have for computer functions, floor is usually something that you cut off below, and then there's also the function ceil that cuts something on the top. Yeah. So cap maybe should cut something on the top, floor should maybe cut something on the bottom. And indeed, this is also how these names are used when you think of, I pay you a coupon. Yeah? So this is a small remark on the name. The name caplet or cap seems maybe a bit counterintuitive, because usually you think that a cap is something like an upper bound and a floor is something like a lower bound. And indeed, this notion is used. Yeah, so I would say the coupon L is kept if the coupon is the minimum of L and K. So this means that we are here in this situation. I pay you L, but when L reaches the K, then I just stop, yeah, and I'm cutting off the upper part. I'm capping the payment. This coupon could be, for example, be paid in a bond. So it is like a floating rate bond, but once the floating rate is above a certain level, it is cut off, it is capped. Or like here in the floor, I'm paying you the maximum of L and K. So it means I pay you L if I'm above, but once if I go below, I'm flooring. So I pay you at least K. So these words are often used when you speak of coupon. I have a capped coupon, I have a floored coupon. So the coupon in a bond can be a complicated function, which is then a so-called structured coupon, yeah? A structured bond or a structured swap. So how does this now relate to these products, the floorlet and the caplet? Well, this comes from the following situation. So think that you have the liability to pay the variable interest rate. So actually, I need to pay the minus L. Then, if I buy a caplet, so if I buy a caplet, that is here the plus maximum L minus K, what I actually get is that instead of paying, yeah, so pay, recall that pay means it is negative for me. Instead of paying now the variable interest rate, I now pay only the capped rate. So I have indeed capped the coupon. So in order to limit your interest rate risk of paying unbounded quantities of interest rate, which you have here, you can limit your interest rate risk, you can cap your interest rate risk by buying a caplet. So put differently, if you have L and you exchange it against the capped L, LK, then this is the caplet. Yeah, okay, you can just check this. So you have L minus the capped L. So this is just the L minus, okay, now capped means I cut it off on the top, means I have the minimum of L and K, so I cut it off. Having the minimum is like minus the maximum of minus L and minus K. Okay, so it is maximum of minus L minus K plus L. So it is my maximum of minus L plus L 0 and L minus K. Yeah, so it's my caplet. Okay, so you see the caplet is the financial product that caps your liability. So that's maybe how you can explain this name. Another nice optional product, yeah, maybe a bit harder compared to the piecewise linear, yeah, that is continuous, yeah, the piecewise linear and continuous function is the digital caplet. So my digital caplet pays the indicator function on L minus K. Okay, so multiplied, yeah, for a given K, multiplied with the period length, the notional amount paid at the end of the period. Okay, that looks complicated. Yeah, I pay you just the indicator, 1 if you are above, 0 if you are below. Also, I pay it later at the end of the period. But there's a nice relation between the digital caplet and the caplet. If you think of your payoff, so my payoff is here is L, and well, here is what do I get at the time when payment is, what do I get? If you think of the payoff function of the cap, it is 0 if you are below K. It is 1, the slope is 1. Actually, it's not 1. The slope is M times the period length if you are above K. So then the payoff of the digital is just the indicator function. This is the derivative. So if you differentiate here 0, you have 0. If you differentiate here this linear function, you get the slope, and the slope is exactly 1 times M times period length. So the digital is the derivative of the cap. The digital caplet is the derivative of the caplet. So I can just differentiate, for example, with respect to K or minus K, because it is minus K, I can just differentiate caplets to get the values of digitals. I can just differentiate caplet values. Okay, I differentiate with respect to K, and because it is L minus K, it goes in the other direction compared here to this axis. So I get a minus out of it. And we have the nice little lemma that the digital caplet value is related to the caplet value. The digital value for the strike K is differentiate the caplet value with respect to K, and multiply with -1. So minus d by dk value of the caplet with strike K. Yeah, the proof, I wrote here exercise. Yeah, it's actually, you need maybe some regularity assumption, yeah, that maybe the underlying has a density. Yeah, then it's just differentiate, switch integration, so switch expectation and differentiation, yeah, so some kind of Fubini. Yeah, but if everything is regular, this is straightforward to prove. What's nice is that you can approximate the derivative by a finite difference. So we have a numerical method, discussed how do you approximate numerically the partial derivative. So I can approximate this by valuing a caplet with a strike that is slightly shifted up. So maybe this here is the caplet at the strike K plus epsilon. And then I take another caplet with a strike that is slightly shifted down. So maybe this guy here is now another caplet. Okay, and then you take, well, the dark queen minus the light queen. Okay, but there's a minus in front, so actually I take the light queen minus the dark queen. Okay, so that this means, what do we get? Well, here both are 0. Here the light queen is still linear, but the dark queen is 0, so I follow the light queen. And here, when I cross this point, the two cancel. Yeah. Okay, so I get something like this. Maybe I draw this in yellow because that is not the final payoff. Okay, so I get something like this. And then I divide by 2 epsilon because this size here is just 2 epsilon, because this here is just 2 epsilon, this slope is 1, yeah, this is 2 epsilon. Okay, so I divide by 2 epsilon to get my digital payoff. So my digital payoff is just this here, and now a little bit stretched, such that I will reach the point equal to 1. Yeah, so this here is 1. Okay, so you see that you can approximate by these two call option profiles. You can approximate something which looks almost like the indicator function. Yeah, it's just that you go here to an epsilon, there to an epsilon. So you approximate this with a piecewise linear function. And this is maybe something that a trader could do if he would like to neutralize the risk when he sells a digital option. Yeah, he could approximate it by buying a so-called call spread. Yeah, spread, the word is often used for something that is a difference, a call spread. One option short, one option long. Yeah, so one with a plus, one with a minus. Very narrow strike, and the only risk that he has then is this here. So sometimes he loses, sometimes he wins, when we are very close to the strike. Okay, so he just requests from the clients a little bit excess amount that covers maybe this risk here. Apart from this, this is like a static replication, yeah? So almost static replication if you request some additional amount. Okay, so here a bit nicer, yeah, the call spread approximation of a digital option, yeah, also works for digital option on other underlyings where you have call options on this underlying at hand. The cap market is important, yeah, so caps are liquid products, but an even more important financial product is the swaption. So the swaption is an option on a swap, and also studying how we will value the swaption is very interesting, because you will also see for the swaption, or when you compare it to the caplet, that the change of numeraire technique is really a very powerful technique, very important. Something you do not so much see if you study equity options, where the numerator is always a deterministic thing. Okay, so the swaption is an option on a swap. A swaption is an option on a swap. So at a certain time, say this is here my Tx, the exercise state. At that time, I can exercise in a swap. So at Tx, I exercise in a swap. And I would like to receive this swap, of course, only when the swap has a positive value. So I check the swap value. Recall maybe the definition of the swap. So here we have the definition of the swap. Yeah, it's 169. Maybe we go to this definition. The swap is on a certain tenor discretization. So this is T1, T2, T3, T4, and so on. On a certain tenor discretization, we exchange floating rates. So here are floating forward rates for the different periods. These are my floating rates. We exchange these guys against, say, a constant fixed swap rate, against a constant fixed swap rate, so something like that. Okay, so this here is my SI, which is often, say, a constant S, so always the same for all periods. And in the context of the swaption, maybe I call it K. So I exchange these guys here, say, against a constant rate. And if you call this constant rate here K, it looks a little bit like having a caplet. And indeed, a swaption on a swap that has a single period. So if I'm just here in, say, this period, if you have just a single period, this is a caplet. But now, this is not like in a cap that you just have a sum of such things. It is that you have the option to receive the whole package. So in a cap, you can decide, I take this one I don't take, this one I take. Here I have an option on the whole package. So I have to value the whole package. So I have to value the swap. I have to value all this, and then I will decide here, do I take the swap or don't, or I leave it. So do I take the swap or I leave it, I take 0. If you recall our little tenor time discretization, so this is my tenor time discretization here, say T1, T2, T3. In what I've written here, well, the exercise state could be somewhere before. Somewhere before you decide, do you like to have that swap? And also there is some kind of notification period that you usually make this decision a little bit before. But in a textbook idealization, usually we consider that we exercise at the starting time of the first period. So we usually have the case that the T exercise, the exercise date is the starting date of the first period. There is also a little bit, a small modification here, how I write the payoff, the value. But exactly this. For other financial products, we have often defined the product pays at a certain time this amount. And then we have valued what is the value of this payment at an earlier time. But paying in time t and having a certain value in time t is actually the same, if there's just this time where something is paid. So if there is a single payment time, at that time, this payment is the value. So in the context of derivative valuation, so valuation, it actually doesn't matter if something is paid or if I observe a value at a certain time. And in this definition, I write that the value of the swaption is given by something that depends on the value of the swap. So there is here the value of the swap that enters into this formula. So when you then exercise, so when you go to our definition of the swap, I decide I take the swap, but the payments of this swap are then further in the future. But put differently, actually it doesn't matter if there are payments in the future or if somebody pays me this amount in this time. Because if he pays me this amount in this time, I can go to the market and buy the swap, which will be exactly the same as receiving the swap. So in the market, there is actually this difference in a financial product. If you receive the underlying financial product that has this value, or if you receive this value in cash. So this is called the settlement. And there is the physical settlement where you will receive the financial product. And there is the cash settlement where you receive just the value of that corresponding financial product. And here in this definition, I have specified the value that we observe at the exercise time Tx. Well, for us, it does not make a difference to the valuation if we have physical settlement or cash settlement. So this is idealized. It does not make a difference because of what I just explained. However, in the market, there could be very subtle differences. And the reason is actually the following, that you have to specify how this value here is obtained. And what I just explained is if you receive the cash amount, you can go to the market and buy the corresponding product. That would be maybe some very neutral way of specifying this value, just observe it on the market. But often these contracts, I mean, they are written contracts, they specify some kind of formula how this cash amount is calculated. So could even be some approximation formula. So in practice, there is the case that for a cash settlement, the contract may specify a specific formula or algorithm that determines the cash amount, and this could introduce some subtle fractions, subtle frictions, so sometimes complicated deviations from actually the value of a physical settled instruments. So could be a formula that specifies how the index is determined. So how is the swap rate calculated, for example. Sometimes also there is a calculation agent involved, so the contract specifies the value of the swap is determined by this institution using this methodology. Okay, so this is a subtle thing. Cash settled swaptions were very much different from physical settled swaption some time ago, but since this is maybe painful work for the quants, for the mathematicians who have to sort all these differences out, it's very nice that the market has cleaned this a little bit up and there's actually no big difference among the two settlement types. The swaption is an important financial product. I already mentioned this, and the reason why this is the case is maybe related to this little example here, the option on a coupon bond. So it looks as if I now have, if I now study or define yet another financial product, I have the option on a coupon bond. Yeah, so what does this mean? Okay, coupon bond, maybe just to recall, I receive a fixed coupon. So there is 1 unit of currency multiplied with a fixed coupon at the end of each period. Yeah? So multiplied with the period length at the end of each period, plus then the notional, and this here is the case where notional is 1, at the end of the last period. So that was our coupon bond. And an option on this bond, where if you just have the option to receive a bond, you would always exercise, because my bond has positive payments, there is nothing to lose. So the option of the coupon bond means that I have the option to buy this coupon bond. So here is my coupon bond, say where I have my fixed coupons here for every period. Yeah, so this is the period start. Then I have the periods, and in the end, I receive this and maybe the last coupon also back. And the option on the bond means I have the option to buy this bond. So I have to pay some amount here. Yeah, so maybe I pay 1 unit of currency here. Or I lend 1 unit of currency. I receive back this 1 unit of currency at the final time. But to compensate for waiting for this, I also receive back the little coupons here. So this is a forward bond. Yeah? So you have a forward bond, so you buy the bond at a future point in time. So maybe my future point in time where I buy it is T1, and then I receive always at the end of the period. Yeah? And now I have the option on the forward bond. So option on the forward bond means I have an option on this whole thing here. I can buy the forward bond, which means I can decide if I pay 1 unit to receive the coupon bond. So I pay 1 unit of currency to receive. Yeah, so pay means there's a minus here. So to receive the coupon bond. So that's a bond option, an option on the forward bond. If you observe that the value of the forward bonds is positive, so it means that you maybe get here larger coupons, for example, compared to floating rate, which would levelize the value to being equal to 1, then you would decide to take it. So this is my forward bond. It's just the coupon bond minus the payment of notional at the beginning. The value of this forward starting bond, so the value of this little yellow block, is actually very much related to the swaption. Okay, what is the value? The value is the value of the coupon bond. So we already studied the value of the coupon bond. It is interpret each coupon as a small zero coupon bond. So multiply with the payment, the zero coupon bond at payment time, plus the last payment. It's the zero coupon bond at the final time. Okay, so these are all my payment times. The value of this initial payment is, of course, also just 1 unit of currency in T1 paid. So with a minus is, of course, also just a zero coupon bond. So this is the value of the forward bond. But now observe that in my single curve theory, so where the forward rate and the zero coupon bonds are all related, what I have here at the end is the value of the floater. So I can actually replace this part here with the sum of paying, because there is a minus, the value of the floater is PT1 minus PTN, Yeah, so you see this here is actually with a minus, yeah, minus paying the forward rate, well, observed at little t, times the period length times the zero coupon bond at the end of the period. So this is the value of the floating rate bond, the value actually of my floater. So it's actually this line here that we have PT1 minus PTN is the sum L times period length times bond at the end of the. Yeah, and the other part is the payment of the fixed coupon here, also is now a sum, the period length and the zero coupon bond. So you see the value of my forward bond, so that was the yellow block where I have the option on, is actually the value of a swaption. So this is just, sorry, a value of the swap. So you see my yellow block is just the value of a swap, and hence I have that the option on the forward starting coupon bond is just a swaption. So an option on a bond is just actually a swaption. Put differently, if also the swap is just the financial product that converts a fixed coupon bond to a floating rate bond, which is something that maybe yeah, a client likes to do that has fixed coupon inflow, but invests in the market on a floating rate basis. You know? If he likes to do this only under certain conditions, then he converts his bond only under certain conditions to the floating rate bond. He would buy a swaption. So you see the swaption is a companion to the bond market that can neutralize risk, yeah, also only one-sided, neutralize certain risk in bonds. Yeah, it's like a bond option. Next step in my collection of definitions of more complicated products, let's go to foreign currencies. I already mentioned this, that we will do this step at some time, and this is a first look into this, what happens if we have different currencies. Let's study the foreign caplet and Quanto Caplet. So the foreign caplet is just a caplet in a foreign currency. A foreign caplet is a caplet in a foreign currency. So now this is the interesting thing. You have to be a little bit careful, because in all these things of martingale measures and numeraires, there's hidden the thing that something is a traded asset. And what you have to distinguish is that a traded asset depends on in which economy are you investing as based in which economy. So you have to judge everything from the point of view of the investor. So if I am a domestic investor, and if all my investments are done in my domestic currencies, the domestic products are traded assets. The foreign products are not traded assets. I cannot buy a foreign product. Okay, that sounds a bit strange, yeah, because I can buy Apple stock, yeah, which is traded in the US. Yeah? I'm based in Euro, and I can buy a stock that is traded on a US stock exchange. But you have to be a little bit careful, because to do this, I have to convert my Euro into the foreign currency. And then with this converted currency, with this converted Euro, I do the foreign transaction. So there is a guy involved here, which is the foreign exchange rate. So what is a traded asset for me is the foreign stock converted to domestic currency with the foreign exchange rate. So the foreign caplet, which means I observe all the quantities now in foreign currency. This is just the foreign forward rate. If I'm now a euro investor, the foreign market is US. It is an US interest rate, US forward rate, created from US zero coupon bonds. So my foreign caplet has this as an underlying. It also has some strike here, of course. So my strike is some constant number here. This is my foreign simple forward rate. And of course, I will also multiply this with a notional, but the notional is denoted in foreign currency. So all this stuff here all this stuff in the blue box is just the caplet in the foreign market. But now, since I am a domestic investor, I will receive this amount and it will be converted to my currency, well, at, of course, payment time. So this is what a foreign currency caplet, if I own it, would pay to a domestic investor. Everything has to be converted into my currency. The funny thing is that this financial product looks complicated, because suddenly there are two stochastic objects involved. The foreign interest rate is possibly stochastic, but also the currency exchange rate is possibly stochastic because I observe it at a future point in time. The thing is, the valuation of this product is very easy. So it's just the same as the domestic caplet. And the valuation of another financial product, the Quanto, which looks simpler, is more complicated. Before we look to the Quanto, let me now make this remark again. I often made this remark before that I like to often consider the units of the quantities to see what's going on. So it's useful to consider units. And that also holds here for this situation. So what we have is we observe domestic quantities, for example, the domestic zero coupon bond, and it has the unit of one domestic currency. We observe an interest rate. So we observe a domestic zero coupon bond, the P, which has the unit of a domestic currency. We observe the forward rate, the domestic forward rate. It has unit 1 divided by time. It is the ratio of two bonds. So it is unitless with respect to the currency, but divided by the period length. So if you multiply with the period length, you have a unitless quantity. We have the foreign bond, the foreign bond, which I would maybe denote with P tilde, where the foreign zero coupon bond has the unit foreign currency. Okay, so that is here my foreign currency bond. And we had on the slide the FX rate, the foreign currency exchange rate. And if you look back, what's happening here, this is a unit in foreign currency. So this guy here is a factor that if I multiply it with a one foreign currency, I get a one domestic currency unit. So it means that my FX rate has the unit divided by foreign multiplied with domestic. So it has the unit DOM divided by foreign. So if you would like to infer, okay, what is the unit now? What is the model here doing? You just look at this payment formula to get the right unit. And of course, here my notional was also specified in foreign currency. So for this FX rate, well, sometimes the market symbols for me as a mathematician, they are sometimes a little bit confusing. Yeah. For example, here in this case, I stated that the FX has the unit, how many domestic do I get for 1 unit of foreign currency, or how many units of domestic currency do I have to pay for 1 unit of foreign currency. And this symbol on the market is then called often DOM4, or sometimes even with a slash, which is then a bit confusing. Yeah, so sometimes it is called for DOM. Did I say DOM4? Okay, sorry. It is called on the market for DOM, and sometimes even a bit confusing with a slash for slash DOM, which looks as if you would divide 1 foreign currency unit by 1 domestic, but it means that you convert from foreign currency to domestic currency. Okay, so this is how you find this symbol on the market. So if you maybe would like to have a look, if you go to some web page here, you see I have looked up the symbol US dollar euro, USD EUR. So this is my symbol here, sometimes USD/euro. But if you look here, it is a price and the currency is in euro. So this here is the euro amount for 1 unit of US dollar. So this is the quantity you have to multiply with 1 US dollar to get the euro. So the physical unit of this is euro divided by US dollar. Okay, so that's a bit confusing. Yeah, you have to check that you have the right units. Also, if we later model the stochastic processes, it makes a difference if you model the Ito process for fx or for 1 divided by fx. Yeah? No, the Ito's formula gives you a change in the drift, yeah, if you have the 1 divided by. So these are different stochastic processes. You have to be a bit careful. So now the Quanto. The Quanto Caplet ratio, yeah, okay, so maybe we have 2 words here. There is the word Quanto and there is the word Caplet. And the Caplet part looks actually like a foreign currency Caplet. So I have M times maximum foreign currency interest rate minus K and 0 times period length paid at the end of the period. So it is like a foreign currency caplet for a foreign currency investor. If it would be a foreign currency caplet for the domestic investor, there should be the conversion to my domestic currency here. And now you see that instead of doing what the market would do, it would pay the foreign currency amount, and then it would convert the foreign currency to my domestic currency using the FX rate at the payment time. They just pay me this amount in euro. So it is like as if I could trade at an US dollar stock exchange, but all the prices that are displayed are euro prices. So if it goes 10% up, it goes 10% up for me. Actually, if you observe the foreign currency price goes 10% up, it doesn't mean that it goes 10% up for me, because for me, I also have to check, has the currency exchange rate changed? So this is exactly the reason why there is this product. You would like to participate in the performance, in the movement of the foreign currency object without having the risk of losing some of this by the stochasticity, by the movements in the FX rate. So it looks like a simplification because this here has some kind of complicated dependency on the correlation. Is this moving up? Is this moving down? There is some multiplication of two random variables. This is correlation, then creating covariance dependency. So you remove this by just paying this amount, and you just brutally convert with a constant conversion factor. Sometimes also this is a difference from 1, but it's just a constant that converts the units. Yeah, so you could think of paying this unitless quantity interest rate multiplied with time with an amount that is in domestic currency. Okay, just convert the M to domestic currency. Doesn't look too complicated, but valuing this financial product is much more complicated. So this is the Quanto Caplet. So the word Quanto refers to the fact that we convert with just a constant conversion factor instead of using the FX rate. So now let's conclude my tour through these options by a remark on options on the backward rate. Yeah, so we had options on the forward rate, the cap, caplet, floorlet. We had an option on a swap, which is an option on a financial product, an option on a bond. What happens now if we have the backward rate? Yeah, we had the forward rate. What happens if we have the backward rate? All these products, they also exist if we consider the backward-looking rate. So my backward-looking rate was the index I. Well, for the period in starting TI, it was some kind of performance observed at the end of the period TI plus 1, then paid at the end of the period. And you can simply create in all these definitions, you can simply replace in all these definitions the L with the I and get a similar product on the backward rate. For a swaption, consider an option on a swap where the swap pays the backward rate instead of the forward rate. So one remark, changing the underlying index in this product will or may affect the valuation of the option. Okay, so now you may think, okay, we had this nice little lemma that the value of paying the backward rate at the end of the period is the same as paying the forward rate at the end of the period if the value is observed before the beginning of the period. So there was this nice little lemma from which we could conclude that the valuation of a swap on the backward rate agrees with the valuation of a swap on the forward rate. So you would think that all these financial products, if you now switch to the backward rate, they have the same valuation formula. This is not true. This is true for the swaption. And this is because of the special form we have defined the swaption. So let's go back. The swaption is an option on the swap where at exercise time, we receive the value of the swap. And now we can plug in this lemma. Since by this lemma, I have that the value of a swap on the backward rate is the same as the value of the swap on the forward rate. If we are before the beginning of the first period, where the backward rate has not yet started to accumulate. So I have that the value of the two swaps agree, hence the value of this option agrees. So for the swaption, indeed, I have the result that the swaption on a swap on the backward rate has the same value as a swaption on a swap on the forward rate. But if we go to, for example, the caplet, we are here. It is an option to receive the index at the end of the period. And here I did not write when we decide. The decision actually is made here. Well, it is FT1 measurable. So the decision is clear at the beginning of the period if you would like to receive this. But if you replace this object here with a backward rate, then this backward rate will still accumulate during the period. And there could be different outcomes, yeah, compared to where your K is. So then this option has a different time where actually the decision becomes clear, namely you decide at the end of the period. So you have a longer option period by that, because there is still a little bit more volatility, you know, going on during that time fraction. So you see replacing here in the caplet the L with the I. Clearly the definition of the financial product is the same. Yeah? So you receive maximum of I minus K and 0 times the period length at the end of the period. But what is actually going on there depends also how the rate behaves in this interval. So we cannot apply our lemma, yeah, so that the two values agree, because that only holds at the beginning of the period. So we have to be a little bit careful for Caplet. The valuation will differ. For a swaption, the valuation agrees since the exercise is before the first period start. And we had this little lemma, yeah, lemma that the value of the floating rate paid at the end of the period and the backward rate paid at the end of the period agrees if the valuation point is before the period start. So that was it for going through some definitions. And yeah, let me quickly go through now a small repetition of valuing a European stock option under a Black-Scholes model. Okay, so you saw now from my session on the interest rate products with optionalities that all these products look very similar to what you know from the theory of option on a stock. Yeah, so the caplet is like a call option, the floorlet a little bit like a put. Yeah, and even for the swaption, we can show in the next session that we can transform it into a form that looks exactly like in that situation, such that under corresponding model assumption, you will end up with Black-Scholes formula, Bachelier formula, depending on which model you choose. To apply this, I would like to make a small repetition on how you derive the Black-Scholes formula, because the way the formula is sometimes derived is a little bit special. Yeah, it is a little bit shaped for the application that you have, for example, a deterministic numeraire. And if you rewrite this derivation a little bit, you will get something which I say is a kind of generalized Black-Scholes formula. And not only this formula looks much nicer, it's much easier to memorize it. It's also immediately applicable to our interest rate options. So let's go through this. Okay, Black-Scholes formula for an equity European call option. So situation is you have two traded products on the market. So there is your bank account B, and this guy is deterministic, and there is your stock S, this guy is stochastic. Your bank account accrues at a deterministic interest rate. So I have dB is R, B, dt. R can depend on time, but it's deterministic. It's a continuously compounded rate. So here interest rates are deterministic. You know the solution of this is exponential integral from 0 to t r of tau d tau. Well, if you have the initial condition, yes, so maybe there should also be the initial condition here. B of 0 is 1 currency unit. Oh yeah, it is here, the initial condition. So I already know how B evolves. So what is my model for S? Well, the Black-Scholes model, so I assume now the Black-Scholes model here, is that S follows a log normal dynamic. So it is an Ito process, mu s dt plus sigma s dw, w, the Brownian motion. Sigma should be larger than 0. If sigma is a constant, it's called the Black-Scholes volatility, but we can later derive an equivalent constant quantity, the Black-Scholes volatility, even for the case where sigma here depends on time. I would like to value a payoff function. The payoff function is that of a call option. Okay, it pays you the maximum of S A minus K and 0. Payment is in time capital T. So not as in our interest rate case, we pay at the same time as we fix the underlying quantity. So I pay you 0 if you are below K. Otherwise, I pay you a linear function in S. I just pay you S minus K. So what are the steps to solve this? We have our universal valuation theorem. The value is given by numeraire at revaluation time times expectation under the equivalent martingale measure of V of t divided by numeraire of t. So we have to choose a numeraire n, and we move to the equivalent martingale measure. So we use Kirsanov theorem, change of measure is a change of drift. So change of measure is a change of drift. Actually, you do not determine the measure, you just determine how does the process look under this measure, how does the drift look under this measure. So we have that S divided by N is a martingale, so I will calculate S divided by B. If I choose now B as numeraire, S divided by B, and that has to be a martingale, so I somehow get a condition for my mu here. Okay, so then if I have this under this probability measure, I just write here this quantity as a function of my model objects, as a function of my S and my B. So of course, my numeraire is now my B, and then I calculate this expectation. I could calculate it numerically, but maybe here I can calculate it analytically. So let's do this very quickly. We have our model for S. So this is my Ito stochastic process, my log normal process. And now I would like to know how does the process look under the equivalent martingale measure Qn if I choose for N my bank account B as numeraire. What I have is that S divided by B is a martingale. So this means that I know that this is a 0 dt plus something dw. But I know the Ito stochastic processes for S and B, so I can use the quotient rule. Yeah, so how does the etostochastic process for S divided by B look like? This is just Ito's lemma to calculate how S divided by B looks like. So this is B1 divided by B times ds. Well, ds is S times mu dt plus S times sigma dw divided by B. So it is S divided by B times mu dt plus sigma dw. Then it is S multiplied with d of 1 divided by B. Okay, so but this is because of the 1 divided by, it's a minus B and then actually B squared, because of the 1 divided by. dB is RB dt, so it is S divided by B R dt. And then I also get all the other second order term. There is an additional second order term from the 1 divided by B, which is here this R dt, and there is a second order term ds d1 divided by B, which is this guy here. Okay, so I do not have to look too carefully to the second order term because I see that all these guys here are actually 0 because there is a dt times dt, a dw times the dt, dt times dt, so all this stuff is 0. So what I have is just the stuff on the top, the ds times 1 divided by b and the S times d1 divided by b, first order part. So I get S divided by b. Maybe I make this blue again here. So b, so I have my S divided by b in front. And I have a mu minus r dt plus sigma dw in this bracket. So, and you see by comparing coefficients, that the mu has to be equal to r. So you know how the process S looks under the equivalent martingale measure. The mu has to be equal to r. So I know how the process S now looks under Qn. So this is my S under Qn. Well, this is not the S under Qn. Actually, let's move to a quantity y, which is the logarithm of S. Okay, why am I doing this? I'm doing this because the process of S is log normal. So I have here an S dt, an S dw. Integrating is complicated. But if I just have constant coefficients here, then integrating is easy. So I just divide by S and observe that ds divided by S is the derivative of the logarithm. So let's have a look at the differential of the logarithm of S. But this guy has another second order term coming from Ito's lemma. So I get the minus 1/2 sigma squared. Okay, so now you can integrate the d log S of t, and you know the probability distribution of logarithm of S. So I have that the logarithm of S of capital T is logarithm of S of 0 plus RT minus 1/2 sigma squared T plus sigma square root of T times a normal distributed random variable. This is now my function of S and B at capital T. So this is now my function at the payoff time. And you can now calculate the expectation of this function analytically to arrive at the Black-Scholes formula. Okay, so maybe I have to finish here. This is just a small recap. Maybe we can recapitulate this again a little bit. You also find in the script how you calculate the expectation. Okay, you know the probability density of the normal distribution. So it's this guy here, yeah, the 1 divided by square root of 2p sigma exponential minus x squared divided by 2 sigma squared. You know the probability density, and you can calculate this integral, which only involves exponential function and a constant, yeah, multiplied with this density analytically. Okay, so there's the calculation here, and you, using some substitution, arrive at the Black-Scholes formula. I will start with this again to show you just 2 small slides, a much nicer generalized Black-Scholes formula, but let's do that next time. Thanks, that was it for today.